Okay, so when you're asked to find the exact trig ratio values using exact values, what you're doing is you're actually using things we know about geometric properties of certain triangles. And the two triangles that we're working with are isosceles and equilateral. So from geometric properties that we know about isosceles and equilateral triangles, that helps get us exact values. So an exact value is where I don't take my calculator and do the cos of 80, and it gives me this decimal that we round to 4 decimal places. It actually is a number that we don't take our calculator and work with. So the first one we're going to look at is an isosceles triangle. Now, because we're working with primary trig ratios, we know that we have to have a right angle triangle. So if this is an isosceles triangle, we know that isosceles triangles, the two sides are equal. And we also know that these two angles then also have to be equal. Now what's special about this is we already know that in a triangle we have 180 degrees. So those circles actually, each one of them is going to be, because we know this 90 here, they're going to be 90 divided by 2, which is 45 degrees. Okay, so special isosceles triangle, right angle isosceles triangle, we note that these angles are 45 degrees. Now that's important because then what we can do is I'm going to actually assign a value to the sides that are equal to each other. And it doesn't matter what actual side what number I actually give them. So if I take this and I just turn it, okay, so now you can see it's much easier to see the isosceles triangle part. I'm going to choose the number 1. So each side that is equal to each other, I'm going to assign the number 1. Could I assign a different number? Yes, I could. It just means that I would then have larger numbers to work with. So if those have a side length of 1, I can find the hypotenuse using Pythagorean theorem. So Pythagorean theorem says c squared equals a squared plus b squared. So in this case, our a's and b's are both the same, so it's 1 squared plus 1 squared, which is 2. So if I'm going to find c, the hypotenuse, that's the same as the square root of 2. So instead of taking my calculator and giving me a decimal value for the square root of 2, I'm going to leave it alone and leave it as square root 2. So that's how I get exact values for a 45-degree triangle. Now what you need to do with that is a couple different things. Because we're working with, and I don't know why that blue thing's there, but that's fine. Okay, sorry for that blue rectangle that's there. I can't seem to make the smart board behave itself. So what I have now is I have exact values for a right angle triangle that's 45 degrees. So what I can do with that is I know, for instance, that sine of 45 degrees I know is going to be the opposite over the hypotenuse, because that's what sine is. So when I look at this triangle, here is my hypotenuse. And it doesn't really matter which 45-degree angle I use. So if I use this one, this is opposite and this is adjacent. So I end up with sine of 45 as being 1 over square root 2. So I'd leave it as 1 over square root 2 because that's an exact value. If I took my calculator and did the sine of 45, it would come out as 0.7071, which is not an exact value. It's a rounded value. The same thing can be said about if I do the cos of 45. I can do that, and it's adjacent over hypotenuse. Again, if I look at the triangle, I know that the adjacent is also 1 over the square root 2. And finally, the tan of 45 is going to be opposite over adjacent, which is opposites 1, adjacents 1 is 1 over 1, which equals the number 1. So for an isosceles right angle triangle, I can get exact values for sine, cos, and tan. So the other triangle we need to look at is an equilateral triangle. Now, think about this. An equilateral triangle, we know that all the sides are equal. Okay, we also know that all the angles are equal. Okay, that's the whole point of an equilateral triangle. But when we're talking about trig ratios, I don't have at the moment a right angle. So one of the special properties about equilateral triangles, I can actually make a right angle triangle by coming down from one of the vertexes, and that creates a right angle. Now what's special about equilateral is when you do that, it divides the angle at the top in half, and it also divides the bottom in half because it's a perpendicular bisector. It bisects it in half. So I'm more interested in now because this has created my 90-degree triangle. So I'm going to take that 90-degree triangle out of there, and I'm just going to look at this part here. So if I look at this part here, this is 60 and this is 30. So just like the isosceles triangle, I can actually assign a value, use Pythagorean theorem then, and the properties of equilateral triangles to come up with exact values for the side lengths. And again, I'm just assigning a number, and that's easy to work with. And so this side here, so I'm going to say it's an equilateral triangle, side length 2. So that means this here is this here, so that's the 2. And because we dropped a perpendicular bisector down, that divides that in half, so this is 1. So this time when I use Pythagorean theorem, I have the C, right? And I want to find either A or B, whatever one you want to say it is. So I would take my C squared minus my B squared, so I would have 2 squared minus 1 squared, which is 4 minus 1, which is 3. So that's A squared, so that means A is the square root of 3. So the reason it's exact is I'm not taking my calculator and taking the square root of it. So now with this triangle, because I know all 3 sides, I can use it 2 different ways. I can use it to talk about a 60-degree triangle. And if that's the case, then I know that this would be hypotenuse, this would be opposite of 60, and this would be the adjacent. Or I can take the same triangle and label it according to the 30-degree angle. And this is 2, this is 1, this is square root. Oh, sorry, that should have been square root 3. Square root 3. And what I would end up with is this time this would be opposite, hypotenuse, and adjacent. So then I can use the formulas for sine of 60 or the sine of 30. And we know that it's opposite over hypotenuse, which would be opposite for the 30 would be 1 over 2, so a half, where sine of 60 would be square root 3 over 2. Okay, so again, I wouldn't take my calculator and do square root 3 divided by 2. I'd leave it as square root 3 over 2. So that's how we get the exact values. So we don't want a decimal answer. Okay, and as you go on in this unit, you know that we don't just keep at 45, 60, and 30, because when we go over to other quadrants, obviously, if I'm over here, this angle is larger than 90 degrees. So that means that how do I use exact values with that? What we do is we actually drop a perpendicular down to the right, to the x-axis each time. And the way I figure out this here is I do 180 minus whatever this angle is here. So say it was 135 minus 135, which would be a 45-degree triangle. So I could use my exact values then to find exact values for the sine of 135, the cos of 135, and the tan of 135 using these triangles, as well as subtracting or adding from the x-axis. Okay, if you need more help with that, just let me know. But that's where the exact values are coming from.